In our last example, we looked at an equilibrium of H2O liquid and H2O gas, noticing that when we changed the amount of heat, we shifted the reaction from one direction to the other. It caused a change in the equilibrium. All right, we upset the equilibrium. That upset was basically we added heat, which was this right here, and that was an increase because we stuffed the bottle in a microwave. That was our initial change to that equilibrium. We caused the shift to shift away from an increase. And when it shifted away, the resulting arrow, the head of this arrow, pointed to what behavior this does. So what I usually remember is the head of the shift arrow points to things that go up. The tail side is going to be aimed at the side that's going to go down. So these are all the responses. In other words, this is my initial change, this is the shift, this is a response, and this is a response. The response is dictated by how the shift arrow points. So just take a step back from this and does it make sense that if you add more heat to liquid water, you get gaseous water? It does make sense, all right? Now we're going to look at another equilibrium here with water, and this is going to be an issue of how do I make ice? Now some people might say, well, Mr. Zakari, it's real simple. If you want to take and make ice, all you have to do is take liquid water and add heat to it, and you'll get ice cubes. Okay, so let's try that out. All right, we're going to put the ice cube tray into the oven. I'm going to leave it in there for a few minutes and see what happens. Okay, so let's pull it out. Oh my God, we got ice. Well, if you believe that, you're insane. All right, just a little trick on you. We didn't actually make ice by putting an ice cube tray in the oven. So when we look at this equilibrium, if I was to increase the heat right here, the shift would shift away, going that way, creating more H2O liquid, all right? And thus, we wouldn't be able to make solid water, all right? Hopefully that kind of makes sense, because if you increase the heat, you're definitely not going to make ice, all right? So what do you know about making ice? Well, if you know about making ice, you know you have to decrease the heat. So in order to decrease heat, we use a thing called a freezer. So here's the freezer. All right, so we're going to throw the ice cube tray in the freezer. And voila, we will eventually get ice. Well, why does that disrupt the equilibrium? I will show you why. Because what you're really doing by putting this into a freezer is you are doing an initial change on this equilibrium to push the heat down. In doing that, you're going to cause the reaction to shift toward a decrease. That's how the stress will work. It'll always go toward a decrease. Once again, the head of this arrow right here points to things that go up. And this side will then go down. All right, so again, we're looking at LeChatliers' principle about changes to a system at equilibrium and how the reaction will shift in response to that change in stress. In these two examples that we've seen, we've changed the heat. We either moved the heat up or down and witnessed the shift, which is the arrow left-right, and how it behaves. In summary, the shift will always go away from an increase, and it will always go toward a decrease. The remaining arrows are the responses to the shift. If the shift arrow, the head of the shift arrow, example, this is the head of the shift arrow, head will point to things that go up, tails will go to the changes that go down. We're going to look at one more example of this using a little boat outside.